Welcome to the Friday Transportation Seminar. My name is Chris Monsieur. I'm an assistant professor here in Civil and Environmental Engineering. And together with my colleagues, Robert Teen, Miguel Filiotti, Jennifer Dill, John Glebe, we co-organized this Friday Transportation Seminar. We're very pleased today to have Ida von Schalkwyk from Oregon State University, one of our partners in the OTREC consortium, to present today on fixed effects of speed photo enforcement on urban freeways in the U.S. So with that, Ida, take it away.
Thank you. Well, welcome everybody. Today I'm going to be talking about something that I did when I was still in Arizona. So I thought that the topic would be really interesting to share with you. We learned a lot in the process. To start off with, I want to acknowledge my two research partners, Professor Simon Washington, who's still at ASU, and then Kangwon Shin, a PhD student. And then ADOT, who gave the money, of course. So I'm going to be talking today about briefly what the program was all about, and then talk about the findings. I was stunned by it. I'm not a big supporter of speed enforcement. Who wants to get a ticket in the mail? And so it was a really interesting project to be involved in. Learned a lot, and I think you'd be surprised to see the results. And then I'm going to present some conclusions, and that will help us move forward in terms of what we want to do on other systems and elsewhere, and whether it's an option. So just as a summary, we know that speeding is seen as a major contributing factor to most crashes. So obviously, one would think, well, we can keep the speeds a little bit lower, then we're going to reduce our fatalities. Okay, that's what we all want, save some lives. The photo radar technologies is not new. It's been used in 75 different countries across the world, some with more benefits than others. But until 2006, the US had not seen an installation of a fixed photo enforcement program or pilot program of any sorts. Mostly because the public didn't really want it. Okay. So the city of Scottsdale said, well, we have this 6 to 8 mile stretch of urban freeway that goes through our city. And for us, that is the most dangerous section of a roadway. And so we want to do something. And so they sat down with ADOT, went through a long process, and ADOT agreed to have them do a pilot project. Just a brief note, City of Scottsdale, there's a lot of red light running enforcement. So their wheels are pretty oiled in terms of processing, citations, the courts. I mean, it works. Okay? So I think that made a big difference in what happened with the project. So they got permission to have a 9-month pilot program over 6.5 miles of the Scottsdale State Route 101. It's an urban freeway, speed limit of about 65 miles per hour. It's that little piece. And what the 101 basically does, for those of you that's not familiar with Arizona, or Phoenix, it has a loop that it makes, and this loop is pretty big. I got lost once when I just moved there, and I thought, oh, I can just keep driving. I'll eventually come to the other side. It took me more than an hour. So it's a pretty big loop, and that's the stretch that we're looking at, and that goes through the city of Scottsdale. Here's just a nice Google Earth view of it. A little bit of a close-up. Here goes the 101. And there's the sites marked out for us. So we have 3 cameras per direction. In the infraction speed, there's 6 installations. 1, 2, 3, 4, 5, 6. And the posted speed limit is 65. And they said they would take the infraction speed as anything from 76 miles per hour. And then criminal speeding, of course, is 85 miles per hour, larger than 85 miles per hour, which you do get in Arizona. Here's just an example of the installation. So there you can see the cameras, and of course they have big signs that says photo enforcement. So one shouldn't get caught in it without knowing you're going to get in trouble. For the analysis, we had an interesting process. Usually you have a before and after. In this case, we had a before period where we had no speed data really. So we had crash data and volume data. Then you had your warning period where they switched on the cameras were flashing, and they were mailing out things that looked like citations, but it was kind of warning. Hey, we saw you doing things that you weren't supposed to do. The actual program was 244 days. And then we had a brief period where the system was switched off. Cameras were back closed. And big arguments, are we going to go ahead? Are we going to get permission to go ahead? And sure enough, they got permission to go ahead. And so we have a reactivation period. So what made this really nice is that we actually had 2 periods in which we could see whether the performance of the system is consistent. So I'll tell you a little bit about that in just a bit. So in terms of evaluating the program, we looked at 3 basic things: speeding, and we called it detection frequencies, anything over 75 miles per hour. And then we also looked at average speeds. Unfortunately, sometimes in research, you get given a program that's about to start. So we got the program right before the before period, the warning period. And they didn't ask us, what data should we be collecting? They just said, oh, we're starting, and this is what we're giving you. And what they gave us was average speeds over a 15-minute period. So unfortunately, not individual speeds by lane, which was a headache. But we worked with it, and you'll be surprised at the results. Then we also looked at safety. Crash reduction, obviously, big deal for the program, because that's ultimately the goal. It's not about making money. And then the socioeconomic savings that comes with that. And then Carmen focused a little bit on travel time. I'm not going to talk about travel time, except mention it when we get to the conclusions. So I love this graph when we finally got it together, because what you see is you've got the before period right here. You see that little blip? One of the radio stations said, let's see how many warnings you can get in the mail. The one that gets the most gets some sort of a prize. So the people worked really hard to get citations. So when you're working with an enforcement type project that you're evaluating, what the press say and do and what goes on behind the scenes are really important. So something to consider. And then we have our program period. Then we have the deactivation period, where the detection frequency daily per camera increased by 10-fold. Then they didn't give us that last bit of data, and then they reactivated the program. And these blips that you will see, that's all weekend and holiday effects. And in that area, we established that a weekend day is much like a holiday. So they performed about equally in terms of characteristics. So let's look at the numbers. Yes, we had significant reductions during the program on weekdays, and then also so the warning period and the program period. So when we were sending out notices and saying, we saw you doing things that you shouldn't be doing, and when people were actually getting tickets, significant difference. And then also in the deactivation period compared to when the cameras were actually working and giving out citations, significant difference of almost over 1,000 per day per camera. So big, big, big volumes. And in weekends and holidays, much higher differences in terms of what the camera actually did. And the dark blocks show significant differences. So what I liked, what they didn't highlight though in our report, is the fact that if I compare what happened during the reactivation period and the period where we had the pilot, it's basically the same. So the system performed similarly, whether it was the actual preliminary period where we were just looking at how the system was working, compared to, okay, now we're really implementing it as something that's going to be there for a long, long time. Okay, and this slide is especially for the traffic engineers that loves the flow and density and speed graphs. You should feel warm and fuzzy right now. So we all know this relationship between speed and flow. What we did is if you sit down a little bit and you start thinking about speed enforcement, you quickly realize that the only time when the camera is going to make a difference is when I have sort of free flow speeds, or speeds that I can at least bring down. If congestion is slowing down traffic, then obviously the camera, can the camera do anything? Can't do anything. It can't do anything to my speeds, and it can't do anything to my safety. So it had a big impact in terms of the design of the evaluation project. So the before period, all these gray little dots, and then during the program, a very nice tight band of observations. So for the traffic engineering students in the audience, what is that graph telling you in terms of speed dispersion? Ah, you thought you were just going to listen. Yes?
Not a traffic engineering student or a civil engineer, just a public administration student. But you look at that, and it looks like what you're getting is a majority of your traffic is going to the peak flow. So you're keeping all of your cars moving as quickly as they can. I mean, it tops out right at 76, it looks like. So.
Mm-hmm. Okay, so what about one of the transportation graph students? If you look at that graph, you can see that the amount of speed dispersion has reduced quite a bit. So the band of variation in speed has reduced. And we know that there's a direct relationship between that and your speed differential and crash outcomes. So something that we were really, really happy about when we look at the results. Here's just another warm and fuzzy graph. If you look at the before period and we look at mean speed, this was our distribution. And we managed to, with the cameras, get it in a really nice tight band. It's nice. Yeah. No, I was really, really impressed. That.
Can you clarify?
Yes.
Are those 15-minute speeds?
Yes. So the observations that we got was average speed over a 15-minute period for all the lanes. Okay. And I have to say, on that urban freeway section, you don't have a big variation between the speeds in the slow lane and the fast lane. Not enormous to really distort it. Well, right. So what was basically happening is at least 3 of the cameras had the cameras right close to the interchanges, so you didn't have anything happening in between, but relatively closely spaced. Okay, then moving on to what we've seen with the mean speeds. So obviously, as volumes decrease, I'm going to get a bigger speed reduction. Okay, that's just That's how relationships work. So we confirmed the traffic engineering relationships over again. Then we saw that the mean speed decreased by 9.97 miles per hour, almost 10 miles per hour when the volume was really, really low. And then it reduced by about 8.47 miles per hour when the volume was relatively high, on the high end. And that's vehicles per lane per hour. So we've seen a difference in terms of speed. So what happened with crashes? So before we can look at crashes, we really need to see what's the crashes that I can really change with the cameras. We call them target crashes. So we looked at 3 basic groups of crashes, although we did evaluate the whole group as a whole, and that was rear ends, side swipes, and in single vehicles. Why would we be really interested in single vehicle crashes?
Speeding definitely causes an increase.
Okay, so how is single vehicle crashes different from rear end crashes? There's a distinct difference.
Just a guess, but rear end would tend to have to do more with congestion, and single vehicles could have to do with high speeds and loss of control.
Right, but the single vehicle crashes are much more severe, generally. Rear ends, you get some bad rear ends, but usually it's the single vehicle crashes where we lose a lot of people in the system. So that's one reason why we pulled this out. The rear end crashes we pulled in specifically to account for anecdotal discussions that the cameras were causing localized braking, and that would increase the amount of rear end crashes. So we wanted to isolate that crash type so that we could actually look and see did it make a difference or not. And then the same thing as we did with the speeds, we did with the crashes, and said there's a time period where these cameras can make a difference, even if they want to. So we looked at offbeat crashes using time of day as a surrogate. So we had blocks of time that we did not include. And then obviously all weekends, all holidays were included. And we broke down the crashes by those 4 groups. So that was our target crashes. And then we applied 3 different before and after study methodologies, and we started at the most basic, where we're just adjusting for differences in flows. And I wanted to show you this before I move on. Over the 2001 to 2006 time period, we saw a rapid increase in the growth of volume on the 101. And so it was necessary to bring in adjustments for volume. So here we assume the only change that occurred is basically the volumes, traffic flow. Then in the second approach, we said, okay, so sometimes we have systematic changes that occurs on our network. Let me use an example that we all can kind of associate with. I was working with WashDOT on a project where we looked at 2-lane rural roads. And somebody mentioned that there was concerns about motorcycle crashes that may be increasing. And so big discussions, what's going on? And well, guess what? Motorcycle crashes has been increasing nationwide. Why? Because we're seeing shifts in modes. People tend to get on their motorcycles because they don't use as much gas as a motor vehicle do. So instead of blaming the 2-lane rural roads for what's been happening with the motorcycle crashes, we know that there is a systematic increase. So we don't place that increase on what's happening with that facility, but rather what's happening with the system. So this is exactly what we did in 2. And so the comparison zone that we had was somewhere around here. And so it's relatively far away. You can't really have spill effects that affects it. And so we thought that that zone would be a good area to compare it with. And then last but not least, we did the empirical base before-after study, which is widely recognized as one of the better approaches to do before and after studies. And what that does, it allows for correction for regression to the mean. So who can tell me what regression to the mean means? Okay, so I'm expecting a baby. Let's say I have 5 kids. On average, those 5 kids will be as tall as me and my partner. If it's not, and they all taller, and that happens with the whole population is going to get taller. Or the whole population is going to get less tall. Okay? But when I look at my kids are going to be tall, and there's going to be shorter ones. Wide range. So with crashes are random and rare events. And without doing anything to the system, no changes to volumes, say I have the same people driving on the road exactly the same time, everything's the same, weather, everything. The crashes will randomly fluctuate around the mean. So I'm going to have a low year and a high year without doing anything. So what we want to make sure is when we do the before and after studies is that we don't catch a high year and then we implement something and we catch a low year and then we say, oh, the change was because I did this thing. Okay? So that's the whole purpose of the empirical based process. So what you do is you have your observed crashes in your before period, and then you have your observed crashes in the after period. Now in the old days, we would just say, this one minus that one, that's the benefit. Okay? And if it was negative, we said it didn't reduce crashes, it actually increased crashes. What we're now doing is we're using our comparison sites, so similar sites, and we make a prediction of the expected amount of crashes without the measure. And so when we take that difference, that is the estimated average reduction in crashes for sites that looks like this. Okay. So what did we find? We found some really nice stuff. That single vehicle crashes, side swipes, and your overall crashes all reduced. And it reduced over the injury category, so all crashes involving one or more injuries, and then also those that had just property damage. Very, very nice. What did we see with the rear ends? With the more basic before and after studies, some showed an increase in rear end crashes. But consistently, that change, whether it was a reduction or an increase, was not statistically significant. So the claim that people were braking localized and that would increase rear end crashes, we refuted that one. Didn't happen. So something else that's not really visible with a graph like that I was very excited about to see was that the severity distribution of the different crash types also reduced. So if I had single vehicle crashes before, say, and I'm just making up these numbers, say 30% were fatal 40% were injury, and the remainder was property damage only. All of a sudden, we had small portion of fatal. In fact, we didn't have any fatals over the after period or the program period. But all the big things that we wanted to reduce, their portions got smaller. So very, very exciting. Hard for me to believe, so we did send the student back and say, you need to check those numbers, because I don't believe them. So careful check, careful check. So now we know that the system brought down the mean speeds. The system did change our crashes for the better, and in fact, huge reductions in terms of crash frequencies and injuries and potentially fatalities. And now we get into the money. They say money isn't everything, but it sure makes the world go round. Okay? So any program like this costs money. Having the cameras out there, having the measuring equipment, having the system run costs money. So we have to show whether there's any economic benefit or not. And the benefit that we looked at was not revenue, but saving in lives and injuries. So very exciting. We used the Arizona Codes Project, which I was the lead researcher on, where we have a lot of fun linking crash data with medical data using probabilistic linkage. So what does that mean? I don't have a unique number that's on my crash report that's also on my medical reports at the hospital. So I have to go through a statistical process to say, if I had 3 males, 53-year-olds, they were in crashes in this region. And then I have a 53-year-old that checked into the hospital that was in a motor vehicle crash. What's the chance that one of those were the person that's in the hospital? And how does it differ between the 3 individuals that were in crashes that evening? Okay. But very, very neat. We end up getting not only Arizona-specific crash costs, but costs for urban freeways in the Phoenix area in Arizona. And by crash type and by severity. And I believe this is the first time in the country that this has ever been done. So we were very excited, looked really carefully at the numbers, and it all made sense. So how do we get to those numbers? NHTSA is the sponsor of Codes Projects, and they had one of their code states develop a process whereby we use the medical information, the AIS score. Who knows what the AIS score is? It's the abbreviated injury score, which is a much better measure than the CAPCO scale to actually give you crash costs. And it used a range of research, really solid foundation for those numbers. So it's not just numbers that we just made up. Now this is the worst possible slide you can put up there. Okay. I always say to my students, this is a slide you should not put up. But the numbers are so cool, I really wanted to show you. Let's have a look at our rear end crashes. Now, has anybody of you been in a rear end? Okay, so I see a few hands. Did everybody kind of walk away from the crash? Nobody died? Nobody went to the hospital? Who has neck and back problems? Okay, who at least went a couple of times to a chiropractor or the physical therapist or had to drink a lot of muscle relaxants? Okay, so rear ends are those crashes where we say, oh yeah, you know, they're less severe than the other ones. Mostly property damage only. What we've seen in the medical data, though, is that people walk away from the crash, and then the next day, they go back to the hospital. And they say, okay, I don't feel so good. And when we look at the crash costs for property damage only rear-end crashes, I got some really high probability links, so I was really happy with my links in terms of the statistical evidence that it is indeed a good link. And you'll see that the total cost of a property damage only rear-end crash ended up being $224,000. Yes? That's urban freeway conditions in the Phoenix area. And that is because a lot of people that's involved in rear-end crashes are battling not only right after the crash, but they have continued issues with their backs and necks and muscular system. So, and when you look at the other crashes, you can see, you know, if you have a single vehicle property damage only, we're talking about 107,000. Big difference. If you look at the scales. Okay. So we were pretty happy in terms of evaluating the cost and seeing whether it really made sense. And then, of course, the cost includes the final medical cost. Then there's quality of life cost that gets brought in. And then there's other costs, such as the insurance companies, administrative costs that they have, the emergency services, and so on. That's all the other costs that came in. So what was our finding? That the project, on an annual basis, saved us $17 million. That is only in terms of crashes. Now, who likes an investment like that? Okay? You show that to any businessman, they're going to say, this is a good deal. 6 cameras working for a year, $17 million. Yes?
And it include the cost of implementation? What was the cost?
So we did not go into that side of the project at all. We had no information in terms of what it costed, what it's costing in the system. They're definitely not making a loss. So the revenue that they're generating from the tickets are paying for the court, the processing of the citations, the cameras, and so on. So, but a pretty good investment, don't you think? So, let's go to the conclusions. So, the speeding detection, so that's for speeds over 75 miles per hour, increased by a factor of almost 11 times when the cameras were switched off. So drivers do change their behavior based on the expectation that there's going to be enforcement. Okay. So we don't want to drive at the speed limit, but sure enough, if we know there's a big chance that I'm going to get a ticket, then I change my behavior. So we can conclude that the process did deter the drivers from going to speeds that's higher than 75 miles per hour. No evidence of spillover at all in any way. Average speeds, reductions around about 9 to 10 miles per hour. And then the speed dispersion, very, very important. That got smaller, which makes us really happy. Both in terms of what's happening with flow, so your flow is more consistent, and then also in terms of crashes. Target crashes, so overall the crashes reduced by about 54%, injury crashes by about 48%, property damage only by about 56%. Great reductions, and it's just really stuff to get excited about. And in the rear ends that we did see either an increase or a decrease with the procedures, it was not statistically significant. So those crashes just didn't change. Yes? Okay.
Even though the number of rear-end crashes weren't reduced, what, say the severity of those crashes, was that reduced?
The severity distribution did reduce, yes. Whether that is statistically significant or not, that we didn't know, because the sample sizes get really, really small when you kind of look at that smaller breakdown. Wait, okay, what just happened? It's that surprise, surprise. Okay, I guess it wants me to finish up. Let me see. Okay. Let's see. Okay, so let's quickly run through. Unfortunately, I don't have one that can kind of skip in bigger blocks. Okay. There we go. Now, what we did see was that there was swapping of crashes. So, where my single vehicle crashes reduced, I had that slight increase in the rear ends. And that is a common thing that happens when we have countermeasures. So, who can tell me what happens when I have a new traffic signal? What happens with my crashes? Okay, so which ones are going to increase and which ones are going to decrease? Rear end will increase, and what will reduce? At an intersection, a signalized intersection. Yes?
Dr. Bertini is hinting at maybe T-bone crashes.
Yes, that right angle crashes. And we like that swap because, again, we're swapping between a more severe crash type, the right angled, where we get hit on the side of the vehicle that doesn't really have a lot of protection, versus a rear end. Right, so that's acceptable to us because overall we know that the safety is improved. And then that wonderful 17 million annualized benefit in terms of crash costs that we found really showed that this was a good investment in terms of socioeconomic benefit. Okay, so in terms of the travel time, I told you I was not going to give you a lot of detail about the analysis. What Kangwon found was that there was no real difference in terms of travel time. And the reason why we looked at travel time is we went to these wonderful city council meetings. Who's been to a city council meeting? Who's been to a city council meeting as a traffic engineer or as an expert witness making a presentation? I can tell you it's a lot of fun because you have people in the audience that are sometimes biased. And so when we made our presentation to the city of Scottsdale, we had some members of the public that said, well, you know, those cameras are really slowing me down. So because the cameras are slowing me down, I have an increase in my travel time, and so that's costing me money. That was kind of an odd argument for me. But then again, I am a safety person, so I couldn't really see how you could trade off travel time with safety, but granted. So we had to look at the travel time, and Kangwon went through a lot of effort to do traffic simulation and get everything calibrated, and no real difference in terms of travel time. So the whole argument that photo enforcement is going to slow you down and cost money in terms of travel time was defeated. So that was the fixed photo enforcement program in Scottsdale on the 101. Any questions? Yes.
Did you advertise what the infraction speed was? It looks like everyone was driving just under 65 miles an hour, but the infraction was 75 or above. Did they know it was 75 or above, or did they think it was 65?
It wasn't widely publicized, and but my guess was that people would kind of know if they keep below that plus 10 miles per hour, then they'll be fine. But yeah, I think people just weren't really careful. And what was interesting, though, now that you mention it, if we go back to do the home thing. When you look at what happened during the preliminary phase of, let's see how it works, and then the reactivation, there wasn't a big difference between the two. So it wasn't like people initially were really, really afraid and kept to that 65 miles per hour, and then later on realized, but I can get away with a little bit extra. No difference. So yeah, it was surprising. Yes.
Would you say more about the spillover effects that you spill over to other roads, or how about other parts of 101 road? Were still speeding as much there?
They were still speeding as much there. And that is the disadvantage of having that fixed photo enforcement. It's a fixed installation. People know exactly where it is. And I'm from South Africa, and they don't warn you. They don't put up signs. So here they warn you, and you can see the cameras. It's right there. So that's a disadvantage. So you'll see that when the final report comes out from ADOT, is that we have a piece in there in terms of advice in terms of moving forward. And one of the things that we recommend is consideration of going to more a space mean speed approach. So what you do is you measure the average speed of a particular vehicle across a segment of the facility rather than having those spot speeds. And the thought was that if we do that, we would get more stability in the flow. So those people that do brake, speed up, brake, speed up. It's crazy watching some individuals. They actually do that, but that would take that out of the picture and actually improve and maybe even have a spillover effect. But yeah, that's one of the major disadvantages. Yes?
My question was actually right along those lines. When I was in Italy, they have those space, I'm sorry, I can't remember the name again.
More of a space mean speed approach.
Space mean speed. And I noticed that they had it specifically on freeways that had very few off-ramps and on-ramps.
Okay.
But it was a very long distance. I want to say maybe more than 30K or around that far.
Right.
And I was just wondering if any of those installations are in the U.S., if you're aware of.
There's, as far as I know, there's not installations like that in the U.S. And the challenge for us is exactly what you now mentioned, is that they have very few on and off ramps where they're doing that. And so when we're looking at interchange spacing of about a mile, that becomes a challenge, because that means you need to measure between every single interchange, and it's every single mile, so it's not as effective as having 5 or 10 or 20 miles. So yeah, anywhere where people can get off before you can measure them, not a good thing. Because we all try and JPO the system. Yes, Rob.
There are a couple questions from some web viewers, and one of them was, if you think about travel time savings as a benefit due to reduced accidents, and the other question was, you described many positive outcomes, and the one of the viewers was asking, were there any negatives that you found?
Okay. Okay. So the first question had to do with the whole travel time issue, and I'm going to bring up the conclusions that I kind of just browsed over in terms of Kongwon's work. Yes. He had a look at different scenarios of, so in terms of just travel time, no real difference. Then we made the argument that if an incident occurs, so if a crash occurs, then you're going to have delays. So if I have a system that's reducing crashes, then I also have a reduction in the likelihood of having these incidents that's going to cause delays. And so he looked at the one-lane block crash rate. So if I had a crash that blocked one lane, and then I had another crash that blocked 2 lanes. And so he did find that there were travel time reductions because of that in the system. It's difficult, though, to estimate, how many of these would occur. We've got, I think, right across the country, we've got a challenge in terms of data collection with incidents and, what's kind of the average effect and so on. So that kind of data wasn't available, but we did show that there was some travel time savings that's very likely because of the prevention of crashes. Then the second question, Rob, maybe you can.
Oh, were there
repeat
any
that?
negative outcomes? And maybe I'll tack on to that another question that just came in that relates to user acceptance. Any evidence along those lines?
Okay. So what was really surprising was that the community really embraced this. In Scottsdale, there was about an 80% support for the whole process. Now, if you look statewide, the picture looked a little bit different. About half the population that was sampled felt this was the right thing to do. It's for safety, so we're making a difference there. And then the other ones were saying, we don't like it, we're concerned about privacy, and all you want to do is make money. But the acceptance was just incredible. I mean, when we came out with the initial results to show that there were crash reductions, the public just turned around and said, well, this is what we need to do. So we were really, really surprised about that. So yeah, in terms of negative effects, there wasn't really any. I think maybe just the stress levels of the city council when they had these public hearings. But the overwhelming support of even the people standing up at these meetings and saying, this is what we need to do, because they had a vote to get somebody to go and sit down with ADOT to ask for reactivation. And, even at that meeting, people were saying, we have to do this. I know one council member did not exactly like it. He made it very clear that the only reason why he's supporting it is because his constituents support it, but he personally does not support it. But yeah, I don't know of any negative effects that we could have detected. Yes?
You mentioned that that the observations of speeds were much more clustered with the traffic lights on.
Right.
There was much less variance in speed, and yet the rear end there was really no change in rear end crashes. What kind of crashes would you expect to be reduced, given that there was less variance in speed with the cameras on?
Very good question. The research that I'm aware of, and maybe Chris can help me out if he knows about other research, but the research that I'm aware of just looked at crashes overall and said that there was a direct relationship between the amount of speed dispersion and what we see in terms of crashes occurring. So, Chris, do you know about any research for specific crash types?
Yeah, there's some stuff that people have looked at with truck speeds. So with the truck speeds being different, 55 to 65. Some studies found effects there and some didn't. So it's kind of still, what I know of, not quite conclusive, I guess, on the speed dispersion issue.
A big challenge in safety is when we start looking at the crash type level our sample sizes get really small, and so somebody may have studied it, but they can't get statistically significant results. So what can you really report? Well, I've got nothing to report. But a very good question, something to consider. Yes.
I just wonder, on what basis do you decide the location of the camera, and if it becomes invisible to the drivers and only that the freeway is enforced, would that make it better?
Okay, very good. Two very good questions. So the location of the cameras, I think, is critical, and they obviously just went in and put in the cameras. They didn't consult with researchers in terms of which would be ideal places to put it. As a traffic engineer, my best guess would be you'd like to put it where you're getting these free flow speed conditions. So a little bit further away from the interchanges. That spot where you're not really having to concentrate about going slower because somebody's merging or diverging or something like that. What was the other question?
Become invisible to the drivers.
So when you have enforcement where the individual is not aware of the exact position of the measuring equipment, my educated guess would definitely be that would be ideal. Okay. In terms of motivation for the drivers to reduce their speeds. But then there has to be a real risk of getting a ticket, not just some. So, yes.
I had a couple other questions come in from the web, and one of them kind of spins off of a question that I was asking, or I was thinking about. Kind of complicated. Why do you think Arizona was the first location for this to be implemented in the U.S. and I'm sure in your report you'll be recommending some sort of ingredients for success for other agencies who want to do this.
Right.
But maybe you could just comment on what do you think are the ingredients of success, and maybe also did Arizona have to change any state laws to make this possible? Because I know in other states like Oregon, I think it would require some sort of state law change. And are you aware of any other places that are considering such an implementation?
Very good question. I was surprised. And then once I started talking to members of the public and colleagues, I said, oh, well, in Arizona, if there's the political will, now, nobody can argue that Scottsdale is one of the most affluent areas in Arizona. And in the Maricopa County, which is the greater Phoenix area, there's definitely a powerful voice. So I think that political will makes a big difference in terms of whether the political will is there. I was surprised at the support of the public. I don't know whether Scottsdale maybe had engaged in awareness type communication with their public to let them know that this is all about safety. That I don't know. It may be that because that region has a lot of red light running cameras and it's been going on for years, that acceptance comes from, well, we kind of know what we're leading ourselves into. So yeah, that's my best guess with that. Ingredients for success. I would say the first and foremost would be place the cameras where the real need exists. We had an interesting situation when we did the empirical Bayes analysis, and we looked at the regression to the mean. When we looked at the whole 101, that section of roadway through Scottsdale is not the one that needs it most. Okay, so I'd say do your homework really carefully in terms of where it's really needed. Ideally, we would have to go for that space mean speed approach so you don't have the localized braking and maybe have a bigger chance of spillover effects. Then another key thing, I think, is to have a system that can cope with huge volumes of citations. So a court system that has worked with photo enforcement and knows the loopholes that people try to use to get through the system. I think that made a big difference. In terms of implementing the fixed photo enforcement in the bigger Arizona, that will be a challenge. And that's something that Arizona DOT and the Department of Public Safety has been working really hard at. Because in some counties, there's just not the capacity to deal with the citations. There's also differences in, obviously, the courts and how they approach these tickets. Some may just say, well, I'm not going to fine you for speeding. It's not that big a deal, and others will make it a big deal. So I think that those kind of things, and then just the resources kind of components, big issue. Any more questions? Yes, we've got another one.
I don't think you said anything about legal changes.
No, there were no legal changes made. I am aware of a loophole that you can apply when you do get to court in Arizona, but I don't think I'm going to say it on a webinar that's being broadcasted. I was sitting next to a judge on the plane, and we talked about the project because he asked me, what am I doing? And I said, well, I was working for, at that point, at ASU, and he asked me for my card, and when he saw my name, he said, oh, you're one of the people that evaluated the project. I'm going to talk to you. And so he was also a big supporter, but yeah, he shared some legal advice with me, but I'm going to keep quiet.
Maybe just a last, more of a comment that I share your frustration with the lack of high-resolution data with the 15-minute data. And I hope you're recommending in your report that more detailed data be available in the future.
Right.
It's so critical, and technically it's pretty easy. But we want to thank you very much for your great presentation. But before we do that, I'll just remind everyone that next week we have Professor David Goodstein from Caltech. He's a professor of physics there, and he'll be talking about out of gas, the end of the age of oil. So I hope you'll join us next week, and let's thank Ida for her great presentation.
Thanks.